So we have seen in this entire chapter that substitution and elimination reactions will often be in competition with each other. So how are we to predict the product if these pathways are always in competition? Will it be an SN2 or an E2 reaction or an SN1 or an E1 pathway? And to be honest, in many cases, multiple pathways are indeed happening. But we need to figure out which is the major pathway leading to the major product in each reaction condition. So in this video, we will explore this topic in a very systematic manner. And so there are three things to keep in mind when you predict the products of an alkyl halide reaction. The first is to determine the function of the reagent, whether you have on hand a strong base or a strong nucleophile. The second is to analyze the substrate, and in particular, what is the environment of the leaving group like? Is it a primary alkyl halide or a tertiary alkyl halide, as this will dictate the mechanism it will take. And lastly, after you have determined your mechanism, then you would have to consider the relevant regio and or stereochemistry that you must apply to draw the correct product. Let's go ahead and dive into part 1 and part 2, determining the function of the reagent and analyzing the substrate. For detailed discussion of that third part, you can just go ahead and review the previous lectures. Alright, so the first thing to focus on is what is the function of the reagent? Is your reagent going to be a nucleophile or is it going to be a base? Or both or neither, right? Nucleophilicity is determined by factors like the presence of a high electron density and the polarizability of the atom that the electrons are on. Right? So a full-on negative charge, for example, means a lot of electron density, so that's going to be a good nucleophile. Or the lower your atom is on the periodic table, the larger the atom is, the more electrons it is, so again, more polarizability. So these are things you want to think about when we talk about nucleophilicity. On the other hand, when we talk about basicity, we can refer to our previous chapter on the acid-base chapter. Remember back then we talked about the qualitative and the quantitative approaches to determining basicity. In terms of qualitative analysis, the more stable your base is, the weaker it is. And in terms of quantitative analysis, you want to take a look at your conjugate acid, right? The lower the pKa is, the stronger that acid is, therefore the weaker the base is. Okay, so there's two approaches, and if you want to go ahead and review that chapter, this would be a good time to review. So let's take a look at some examples. The first one that's good to take a look at is this bromine ion, or bromide. So bromide ion is an extremely weak base because we know its conjugate acid, HBr, is a very strong acid, right? A pK of -9. So it would be considered a weak base. And at the same time, that bromide ion can accommodate that negative charge because it is a very large and electronegative atom. Because it is so stable, it is also again considered a weak base. But with those same characteristics, having a high electron density and also being fully negatively charged, it is considered a strong nucleophile. So as you can see here, it's not always that a strong nucleophile is a strong base. In our prime example, bromide ion, it is a weak base but a strong nucleophile. On the other hand, let's take a look at hydride ion. We know that it is a conjugate base of a weak acid, namely H2, so therefore it will be a strong base. However, it is an extremely small atom, and so therefore not polarizable. If it is not polarizable, it doesn't have that electron density to be a good nucleophile. So it is a weak nucleophile, strong base. Alright, so these are two examples, but you can also have examples where something is a strong base and a strong nucleophile, as we have discussed in the previous lecture about the hydroxides and the alkoxides. And then you can also have something that is the weak base and weak nucleophile. So let's go ahead and take a look at some common reagents and help us categorize them. So our first category is when your reagent is a strong base but a weak nucleophile. As we discussed a few minutes ago, the hydride is a strong base and weak nucleophile, and often you can see this in its reagent form as sodium hydride. Two more reagents in the same category is DBN, which stands for 1,5-diaza bicyclo 4,3,0 non-5-ene, so short for DBN, and DBU, short for 1,8-diaza bicyclo 540 undec7-ene. Just be glad we are using its abbreviated names here. But eventually both of these molecules are weak nucleophiles because at the site of those electrons it's too bulky to be good at nucleophilic attack. But at the same time, both of these nitrogen sites here allow this molecule to be a strong base. And the reason for that is upon pronation, that positive charge is resonance stabilized. So the acid is a relatively weak acid, so its conjugate base, the original DBN molecule, is a strong base. So both of these bicyclic nitrogen-containing molecules are examples of strong base and weak nucleophile. Before we move on from this, I have one more example, and we have seen this one already. It is an alkoxide. It is a tert-butyl alkoxide, and as you remember, an alkoxide would usually be a strong base and a strong nucleophile, but in this case, it will only work as a strong base because of its bulky tert-butyl group, limiting its ability for nucleophilic attack. So this is one good exception to the alkoxides. If you want a strong base and a weak nucleophile, you go ahead and use potassium tert-butoxide. So from this class of reagents, you can see here, if you're only good as a strong base, then the reaction that you will promote will be elimination and not substitution. All right, now let's talk about the strong base and strong nucleophile examples. And as I have mentioned, we have already seen these examples. The first is the hydroxide, and then there are the alkoxides, namely methoxide and ethoxide. Of course, you can have any counterion when you write the reagent. For example, you can have KOH, NaOH. These would be the more proper way of writing the reagents with their neutral compounds. One more I want to add to this list is the NH2 ion also. Again, when you have a strong base and a strong nucleophile, you might be in a sticky position because you can have elimination or substitution, and at that point we would have to take a look at the substrate to determine the final outcome. So we'll leave it here for now, and we'll come back to that in part 2. Alright, so now let's talk about the weak base, strong nucleophiles. So essentially, they only function as nucleophiles. We've seen these already. They are the iodide, the bromide, the chloride. So those halogens are conjugate base of very strong acids, so they're not going to be very good as a base, but they are full of electron density, so they are strong nucleophiles. Adding on to this are these sulfides, especially if they are negatively charged, whether it's with a hydrogen or with an alkyl chain. Now, sulfur has such a strong electron density that even if it's in its neutral state, it will also function as a strong nucleophile. And again, these are weak bases because the conjugate acids are relatively strong acids. These are some common reagents of strong nucleophiles. So you would expect them to do what kind of mechanism? A substitution mechanism, right? And our last category here are the really bad reagents. These are the reagents that don't really promote substitution or elimination, really. They're neither strong bases or strong nucleophiles. What are they? They are the water molecule, the alcohol molecules like methanol or ethanol. All right, so we first analyzed the reagent. Now we have to analyze the substrate. This will help us determine which mechanism will dominate. So we're going to go ahead and divide up this table and take a look at it very systematically, where we have the 4 categories of our reagents, and we can compare that with the substrate, whether you have a primary substrate, a secondary substrate, or a tertiary substrate. Let's first take a look at our first column here on the left. If you have a strong base and weak nucleophile, basically you are functioning only as a base, right? So if you are a base, you will go the pathway of the elimination. And on top of that, if you are a strong base, then you're going to be a bimolecular elimination reaction. So that will be E2. And remember, it doesn't matter if you're primary, secondary, or tertiary, E2 reactions will work on all three types of alkyl halide substrates. Now on the flip side of that, let's take a look at the third column here. If you are a weak base but a strong nucleophile, again, that just means you function only as a nucleophile. You would have the substitution pathway dominate, right? And because you are a strong nucleophile, it will be a bimolecular reaction. So that means it's going to be an SN2 reaction. And that's true if you are a primary or secondary alkyl halide. What about if you're a tertiary alkyl halide? Even if you are a strong nucleophile, what happens when you can encounter a tertiary substrate? It's too sterically hindered to allow for the nucleophile to approach in a nucleophilic attack. So instead, you're going to do a unimolecular reaction where you generate a carbocation first and then nucleophilic attack. So what is that? That is the SN1 mechanism. All right, now let's go to the second column here. This is where you have a strong base and a strong nucleophile. So this is where it gets dicey because you can either go substitution or elimination as we have discussed previously. For the primary substrate, the SN2 process is actually very fast, much faster than the E2 mechanism. So the SN2 product will be the dominant species, will be your major product. However, as you move on to the secondary alkyl halide, there is a little bit more steric hindrance, so it's going to slow down that SN2 reaction. So in this case, the E2 mechanism will dominate, so your E2 product will be the major product. And so this trend holds because as you move down the list to a tertiary alkyl halide, it will not allow any nucleophilic attack, so the reagent will mainly act as a base. So it will promote the E2 mechanism solely. All right, and lastly here on our last column, when you have a weak base and a weak nucleophile, you aren't really doing much. It turns out because it's so weak, if you have a primary or secondary alkyl halide, you will have no reaction. Unless, however, if it was allylic or benzylic as we have discussed previously. Now, if it's tertiary, a carbocation is stable enough that it can promote a unimolecular reaction. So you have a fair competition between the E1 mechanism and the SN1 mechanism. One mechanism will eke out the other. So for example, if your product is an elimination product where it's tri or tetra substituted, then you will have the E1 mechanism dominate. And if it's not, then the SN1 product will be the major product. Right, so the goal here is not to memorize this table. The goal here is to prove to yourself that you can rationalize this table and recreate it whenever you need it. So let's go ahead and take a look at some practice examples to help us see how to apply this table. And again, there was that third step of regio and stereochemistry. I'm not going to go over in detail because we have covered that in another video you can review on your own. Let's go ahead and try these two first. So this is a nice chance for you just to pause the video, try this on your own, and then watch the video for the results. All right, so in practice problem A here, we have an alcohol chloride reacting with NaSH. So the first thing you want to take note of is your reagent. So that SH, how would you categorize it? It is only going to act as a nucleophile. All right, and the second thing you want to do is classify your alkyl halide. It is a secondary alkyl halide. All right, so if you have a strong nucleophile with a secondary alkyl halide, what is your mechanism going to be? It's going to be an SN2 mechanism. All right, so recall back what that mechanism entails. It will entail a backside attack. So our SH will be coming from behind now with a dash annotation. Okay, good. How about the second one? Again, we see here that DBN is your strong base. It's a weak nucleophile. And then you have here a primary substrate. What does that tell us? Means it's going to be an E2. All right, so an E2 pathway. There's not much to consider here in terms of regio or stereochemistry, as you only have one type of beta protons. So this will be our only product. All right, let's continue and take a look at more examples. All right, so here are two examples. Go ahead and again pause the video. So notice here that our reagents are, I've added more stuff to the reagent. In the first case, it's NaOH with water, so you can see it written this way. Or if it's written one on top of the arrow and one on the bottom of the arrow, it doesn't really matter. Those are just different ways of writing the reagent. So in this case, water again is nothing, as in not a base or a nucleophile. So we want to focus on the NaOH part. The hydroxide we said was a strong base and a strong nucleophile. All right. So we don't know if it's going to be SN2 or E2 yet. Let's take a look at the substrate. We notice that the substrate here is a tertiary substrate. So that means it's going to be an E2 mechanism because it's too crowded for a nucleophilic attack. So if it's going to be an elimination reaction, we must consider regiochemistry because there are different non-equivalent beta protons here. So we'll take a look at the base. We know that the base is small, so it's not bulky. So therefore, our major product will be an elimination product, but the Zaitsev product. It can go ahead and sneak itself in there to give ourselves the most substituted alkene product. All right, what about in case of practice problem D here? We have water again, which is a weak base and a weak nucleophile, so it's not going to do much. But you do have a tertiary alkyl halide, so you will have a reaction. It might be an E1 or an SN1, right? Let's check to see if it's an E1 mechanism. What product, what kind of substituted alkene will you have? Remember, if it's an elimination reaction, it's always going to have the Zaitsev product as a major product. In this case, it is tri-substituted. So remember, if it's tri or tetra-substituted, E1 will eke out SN1 as a major product. So in this case, it is the E1 that's going to be your preferred pathway. All right, two more here, E and F. All right, let's take a look at letter E here. We got TBOK. Remember that that's going to be a strong base but a weak nucleophile. So it's going to be an E2 reaction. It doesn't really matter about what alkyl substrate we have. It will be an E2 reaction. In any case, it is a secondary alkyl halide. We do have to consider regiochemistry here because we do have a bulky base here in tert butoxide. So it's going to prefer the Hofmann product, where your beta proton on the outside will be the chosen proton to be deprotonated, leaving this alkene as your major product, the Hofmann product. What about F here? All right, so we have our reagent is sodium methoxide and methanol. All right, so methanol seems just to be your solvent here. So the focus here is in that methoxide. So that methoxide is a strong base, but also a strong nucleophile. So we again will have a competition between substitution and elimination. But here we see it's going to be a tertiary alkyl halide, so substitution will not work. So it will be E2 as a major pathway. Again, in this case, we do have a choice of alkene products. Methoxide is a relatively small base, so we're going to have the Zaitsev product as our major product. All right, let's do one last example here. What does the reagent look like to you? It's iodide, so it's going to be a strong nucleophile, and a weak base, so it's going to function as a nucleophile. Take a look at our substrate over here. We do have a tertiary substrate. So even though we have a strong nucleophile, that substrate being tertiary, it will not promote a bimolecular reaction. It will therefore promote the SN1 mechanism. All right, so let's think back about the SN1 mechanism. What kind of products will you have? Right, you can have this backside attack from the iodide giving you this molecule, but remember, because it goes through a carbocation intermediate, you also have its enantiomer. So you will actually have a racemic mixture as your product. So there's a lot more of these you can practice on, and that will help you clarify that table to help you predict the products of an alkyl halide in a substitution or elimination environment. Okay, so that ends our discussion on the substitution and elimination reactions of alkyl halides. But before we wrap this chapter up, let's go off tangent a little bit and talk about substitution reactions of substrates that aren't alkyl halides. There are a lot of similarities, but also key differences that we need to highlight. So let's first start this section taking a look at alcohols. However, it is not as straightforward as we would like. For example, here you may assume that bromide will just do a simple nucleophilic attack on the alcohol and kicking it out, much like in the alkyl halide substrates, giving it this alkyl bromide and the hydroxy byproduct. But remember that that OH group is a bad leaving group, meaning that that hydroxide ion is not going to be stable, it's not going to be happy as is, so it's going to react again in another SN2 fashion, give us back our starting material. And actually is heavy favored to be in the reverse reaction because of that. So this reaction is essentially not going to work. So how do we make it work? Remember that we said that the key problem here is that that alcohol group is not a good leaving group. So we just need to make it a good leaving group. And to do so, we will need to treat that alcohol with acid. So if we want to use bromine as our nucleophile, let's use hydrobromic acid. Essentially, the first step is that alcohol will protonate. We'll just make it simple and use the proton from the hydrobromic acid. Upon protonation, you will have a hydronium ion-like species, which essentially is a water molecule once it leaves, and water is a good leaving group. In this step, bromine would do an SN2 backside nucleophilic attack, kicking out that water group. And again, that water is indeed a stable species. It is going to be a good leaving group. So that's how you can make alcohols good substrate for a substitution reaction, is to treat it with acid. So in this example here, we have a primary substrate. This can also happen with a secondary substrate. And in fact, this can also happen with a tertiary substrate. We would do the same thing. We would treat it with HBr to protonate that alcohol group. And once it's protonated, you have a good leaving group in that water molecule. But again, even if we have a strong nucleophile like that bromine lurking around, it is a tertiary substrate, so we cannot do a direct bimolecular attack. But instead, it's going to prefer the SN1 mechanism, where there's a loss of leaving group first, resulting in a carbocation, followed by that nucleophilic attack of the bromide ion to give us our final substitution product. Now, there are instances where you don't want to submit your alcohol substrate under acidic condition, but you still want to do the substitution reaction. But there is a way around this, and that way is to treat your alcohol with tosyl chloride and turn it into a tosylate group. And remember, tosylate is an example of a sulfonate ion, which is an extremely stable leaving group. And the reason for that is because that negative charge can be spread all around the molecule in resonance structures. And the difference between all these molecules is that R group. If this R group looks like that, this is called the tosylate, abbreviated as OTS. If that R group is a methyl group, it's called a mesylate, abbreviated OMS. If that R group is a CF3 group, it's called triflate, abbreviated OTF. Again, all of these are very stable leaving groups because they are very weak bases, due to the fact that their conjugate acids has a very low pKa. For example, the conjugate acid of the mesylate ion has a pKa of negative 1.9, the tosylate has a pKa of negative 2.8, and the triflate negative 14. So very, very strong conjugate acids, so these are very good leaving groups. So now let's go back to how they work. Alright, so we have established that they are good leaving groups, so let's take a look at the mechanisms. So the reagent we're going to use here is this tosylate or this mesylate chloride. The first thing that will happen is that alcohol is going to attack the nucleophilic center of that sulfur. That sulfur will kick out one of the double bonds to the oxygen. At the same time, the lone pair will kick down to reform that double bond and finally kicking out this chlorine atom. From here, you will have this protonated intermediate. We also have a pyridine as our solvent, and it's going to serve as a base to neutralize our intermediate. And remember, that OTS is now a good leaving group. It is primed for reaction. So now if you throw in any nucleophile, it can go ahead and do a nucleophilic attack at that site, taking out your good leaving group. Now, alcohols can also undergo elimination if you submit it to concentrated sulfuric acid, H2SO4, and heat. So let's draw the mechanism for this. Remember here, due to the leveling effect, concentrated H2SO4 will mostly have its reactive form, the hydronium ion. So again here we're going to go via an E1 mechanism. So we will have a loss of leaving group first. giving us a carbocation. Now with that water around, it will be the only thing that can serve as a base for our E1 mechanism. And because this is an E1 mechanism, our major product will be the more substituted Zaitsev product. Now, one note before we end this chapter here is that many students might propose that once you get to this intermediate, you can just throw in any strong base for an E2 pathway to give you more control. Like, for example, if you want the Hoffman product, you might throw in potassium terbutoxide, for example. But remember, because we are in acidic condition, it is not compatible to add in a base because the acid and base will just neutralize one another. So that pathway is not possible. All right, so lots of things to think about. So that ends our long unit on substitution and elimination reactions. You will see these reactions reappear in subsequent chapters, but this is a good introduction for them and a good place to stop.